Hello, and in the second of these talks, I want to introduce some of the consequences of quantum mechanics on our understanding of how electrons move in atoms. And in particular, two key predictions of quantum mechanics, neither of which is predicted by the classical model of a negatively charged electron orbiting around a positively charged nucleus. These are the two key results from quantum mechanics. Firstly, electrons can only be in certain orbits with certain energy levels. They cannot have an arbitrary energy level and be an arbitrary distance away from the nucleus. There are only certain allowed orbits that electrons can be in. These orbits are grouped together in shells. The inner shell, which is the one closest to the nucleus and has the lowest energy, only has room for 2 electrons. There's one orbit in that shell, and each orbit can only accommodate 2 electrons. The second shell, a little bit further away from the nucleus, that has 4 different orbits in it, and can therefore accommodate 8 electrons. And the third shell, further away again from the nucleus, has 9 orbits in it and can accommodate 18 electrons, because no more than 2 electrons can be in the same orbit at the same time. This second result is actually a consequence of electrons being a type of particle called fermions, and a general rule about fermions that no 2 of them can be in exactly the same state. You might therefore think that there can only be 1 electron in each orbit. But in fact, electrons have a property called spin, and they can either have spin up or spin down. And that means that you can have 2 electrons in each orbit without them being in exactly the same state. One of them with spin up and the other one with spin down. That's the last that I'm going to say about spin. We don't really need it as a concept for this module, but I'm sure some of you will come across a lot more about it later. Now, electrons, like just about anything else, will attempt to minimize their energy where possible. Just like if I drop the pen, it goes down. That's because it has a lower energy closer to the Earth. It is losing energy as it drops. Exactly the same thing is true of electrons in atoms. They will try to move down into the lowest level that they can, with the lowest energy. But you can only have 2 electrons in each orbit, and there are only a discrete number of orbits which have increasing energy as you move away from the nucleus. So, if we have an atom with 11 electrons, then the first shell, which can accommodate 2 electrons, will be full. The second shell, which can accommodate 8 electrons, will also be full. The 1 electron left over has to go into the third shell. This would be the arrangement of electrons in that atom known as the ground state. Every electron has its lowest possible energy. Sometimes atoms are not in the ground state. They've acquired a little bit more energy from somewhere, and some of the electrons have moved up and are now in higher energy orbits. Atoms in excited states like this often return to the ground state by the electrons falling and dropping back into lower energy orbits. I'm sure you'll all have come across the periodic table before. You can think about the groups and the periods in the periodic table in terms of which is the lowest energy shell which has an electron in it, which is occupied in the ground state, and how many electrons there are in that outermost shell. This atom here has shell 1 full, shell 2 full, and 1 electron in shell 3. So shell 3 is the highest energy shell which has an electron in it in the ground state, and that makes this a period 3 element. It has 1 electron in its outermost shell, and that puts it in group 1. If we have a look at this periodic table, therefore, we can see period 3 group 1, that means that our element is sodium. It has 11 electrons in it. 2 electrons in shell 1, a further 8 electrons in shell 2, and 1 electron left over in shell 3. So that puts it in the periodic table there. If there were another 3 electrons in the atom, and another 3 protons in the nucleus, so the whole atom remained electrically neutral, we would have an atom of silicon. And another 2 would give us an atom of sulfur. I've chosen sodium, silicon and sulfur as examples for this series of talks because they're all period 3 elements and they all begin with an S. They're also good examples of, respectively, a conductor, a semiconductor and an insulator. And later on I'll try and explain how the arrangement of electrons in these atoms results in those properties of the bulk material. Next time I'll have a look at sodium in a bit more detail, including some of the best evidence that this quantum mechanical theory is actually correct.